My name is Rajat. I am a developer at Kybol. I'm the architect of Quark, and I also work on the various SQL engines that we offer as a service at Kybol. So my agenda today is to first talk about motivation. Why did we start this project at Kybol? I'm going to walk you through a few use cases where Quark can be helpful. Then I'm going to talk about the architecture and how it can fit into your big data stack. And finally, I'm going to end with the roadmap and the future plans of the project. So this is a simplified version of the data infrastructure at Kybol. I'm going to focus on the right-hand side of the slide where we do different kinds of analysis on the data that we collect. For example, Kybol provides auto-scaling Hadoop clusters, and as part of this, we start and shut down machines all the time. And we keep track of these events, and we use these events for different kinds of analysis. For example, the customer ops team is tracking this data set to see if there are many machines being shut down because the health check failed. The business analysts are using this data set to generate billing reports. And there are a bunch of us developers who are asking what if questions on the same data set. So what we want to encourage is for each of these use cases to use the right SQL engine for your job, as well as optimize the data set for your use case. Right? So this is the equivalent of creating indexes in your databases to optimize your queries. The difference in the big data world is that there is no optimizer for you to automatically choose an index. So so the data engineers are forced to create these indexes or optimized copies and communicate and document that, hey, there is this index or there is a sorted copy of the data which you can use. On the other hand, the analysts have to understand, I can use this optimized copy in these different use cases, and they have to remember to use it, right? And this in large organizations doesn't scale. That's where Quark comes in. Quark is an Uber optimizer for your big data stack. So what it does is it sits between your users and your SQL engines, right? And it keeps track of what are all the indexes, what are all the optimized copies of the data that is there, and it takes the query from the analyst, passes them, and directs the query to the right SQL engine and the right data set. So for example, you want the customer ops team, since they're doing a lot of time series stuff, you want them to use a storage engine like HBase, and you want all the queries to directly go to HBase, right? Similarly, you want your business analyst to use a copy of the data set which is sorted by, let's say, the account ID and the month so that they can quickly generate billing reports. Next, I'm going to walk you through a few use cases to make these ideas more concrete. The main motivation to create indexes or optimized copies is to improve performance. The simplest way to improve performance is by reducing I/O. It's a very common fact that the queries that are there in big data don't reference all the columns in a table, right? So just to give an example, query 3 in the TP-CDS data set scans the complete store sales table, but it only references 3 out of 23 columns. So if you have a copy of the data, like of the store sales table with only these 3 columns, it should run faster. So I ran a simple benchmark to test this out. What I did was I created a copy and I ran query 3 on 3 billion rows. This query finished in about 60 seconds on my setup, and then I started adding extra columns to it, right? So you can see from the graph that the runtime of query 3 increased proportionally as we added more and more extra columns, right? So by the time I added 50 extra columns, the runtime had gone up, is more than 200 seconds. So next what I did was I checked, hey, does this situation occur in real world scenarios? So what I did was I analyzed the workload of one of our top 5 customers. I changed the table name so it's not obvious who it is. This customer submitted about 100,000 queries in the last 2 months. And the tickets table is the most important fact table, and you can see that this table has 265 columns, but only 74 of the columns are being used. And this is not in a single query, it is not in a specific workload, but is across their complete set of queries over the last 2 months. Similarly, support is their most important dimensions table, and they use only 10 out of 33 columns. So if they had a copy of this data set which has only the important attributes, then most of the queries should run much faster. So the next question is, how do you make this happen? Like, how do you deploy this technique in your big data stack, right? So the first step is to go create a table. So what I did was I created a table called narrow store sales, and this has only the 3 columns that are being used in query 3, and I don't want to keep all the data. I only want to keep the last 3 months of the data. Then I went and created a materialized view in Quark, and when Quark sees queries like Q3, what it does is, instead of running these queries on the base store sales table, it redirects these queries to run on the narrow store sales table, right? So so the most obvious question to ask is, this is materialized view. It's a very standard database feature. Why did you have to create a new project to implement this feature, and instead go ahead and implement this feature in one of the open source SQL engines out there? This was a very deliberate decision, and I'll walk you through the thought process that we took in about 5 slides. The next kind of optimization is sorted tables. The first instinct of a data architect is to partition all their big tables based on the most important filter columns or join columns. But sometimes you can't do that. For example, in the TP-Series data set, there is a column called SS item SK, which is being used in many filter and join clauses. But you can't partition by this column because it has too many unique values. So you'll end up with too many directories and too many small files. So instead of that, what you can do is that you can sort the data on this column, use a file format like ORC, and then the ORC reader, or it could be Parquet too, the readers will do a binary search and the query should run faster. So you can see from the graphs that I got at least like anywhere between 20 to 60%, like actually 75% 20 to 70% improvement on the queries that are using these columns. This is the first order effects. So you can get performance improvement immediately, but there's also second order effects. Typically what happens is there's a bunch of caches involved in your big data stack. You'll use a block cache, or you'll use a columnar cache. You'll have file system caches, and if you use this sorted data and if you only read the data that you need, there's much less pressure on these caching systems, so that you should see much better performance improvements in a concurrent workload. Again, the way to deploy this is to create a materialized view, so that when you see queries on SS item SK by the analyst, the queries will automatically get rerouted to the sorted copy of the data. And again, I only want to keep maybe the last 3 months of data. I'm not forced to sort the complete data set. The third trick is denormalize tables. So if you are joining a couple of tables all the time, it makes sense to just keep a copy of it around. For example, in the TP-Series data set, there's the store sales and the items table. So what I did was I created a copy of this table, kept it around, and I got anywhere between 10 to 80% improvement. Right now, Quark only supports star schema joins. That means foreign key, primary key joins. And again, you can use a materialized view to deploy this technique into your stack, right? So you specify the joins. You again say, hey, I'm only going to do this for the last 3 months, and you give it the table where this materialized view is stored. The fourth one is cubes. It's a pretty standard feature in the database world. Quark supports cubes that are stored in normal relational tables. We have put in some effort into making the management of cubes much easier. So what you can do is you can create cubes only on partial data again. You can say, I have pre-aggregated the data on only the last 3 months of my store sales table, right? We also support incremental refreshes of cubes. So what you can do is you can pre-aggregate the data only for yesterday, load that into cube, and delete any data that is older than 3 months, for example. So you don't have to pre-calculate it again and again every single day. So, so next I want to talk about why we started a new project. All these ideas are pretty standard. It's been around for quite some time, and it's very possible. It's very easy to implement these features in projects like Hive and Pressure and so on and so forth. But what we realized was, even though these ideas are old and they're very similar, the implementation details are very, very different. So we have customers who are okay with keeping these materialized views or cubes in S3 and access it through Hive. Some of them want to access it through Presto so that they get much better performance over Hive on MR. Some of them have optimized clusters of Vertica or Redshift lying around, and they want to keep the materialized views or cubes in that. Some of them have workloads which are heavy on lookup or range queries, and they want to keep these data sets in a storage engine like Headspace, right? So the point is that the customers want to make a choice on the execution engine and the storage layer, but they want an optimizer that will help them use this, right? So that's what Quark is. Quark is just the optimizer, and it lets you choose the storage engine and the execution engine that you want. And so Quark is a very simple server which contains a cost-based optimizer, and it can reroute queries to the right SQL engine for you. I also want to talk about a slightly different type of use case. It happened, and I'm going to do that using an example. So for example, the store sales table has a sold date column, and the sold date column is used in many queries as a filter class. But for some reason, the data architect has decided to partition these tables on year and month. So what happens is, whenever analysts write queries and they use the sold date table in the filter class, the query goes and does a full table scan. So instead, what Quark lets you do is to specify functional dependencies between the sold date table, sold date column and the year and month column, so that Quark can figure out what exact predicates to inject on the partition columns. So it will, and because of this, it can avoid a full table scan, even though the analysts are not specifying the partition columns in the filter classes, right? This trick can also be used to stop runaway queries. What data engineers can do is say that if I don't see any predicates on partition columns, I'm going to inject some predicate. I'm going to say that I'm not going to let you scan more than a month's worth of data if you forgot to add filters on partition columns. So these were the 4 or 5 use cases that we've seen some traction in Quark. Next, I'm going to talk about how Quark is how Quark stands compared to, let's say, Kylin and Lens. Kylin and Lens also do have some of these features, especially cubes. Also, both Kylin and Lens bring different technologies together to be able to speed up your queries. The main important points are the first two. Those are the fundamental differences. First of all, Quark supports use cases that are not cubes. We also want to support materialized views, and we feel that materialized views are really, really powerful features to be able to improve the performance of a whole number of queries. We've also found predicate injections to be useful to stop runaway queries, and these are features that are not supported, or it's not possible to support in the other projects. The second one is that Quark encourages a mix of storage and SQL engines. Kylin, for example, has made the choice for you, like it's Hive and Headspace. But what we see is that our customers want the freedom to choose the SQL and storage engine for themselves. The others are mainly implementation details, and I know that, for example, the Apache Lens project is working on making the SQL ANSI compliant. So so it's it's mainly implementation details, and it's not that important. But the first two are the fundamental differences between Quark and the other projects out there. So next I'm going to talk about how we build Quark. As I mentioned before, Quark is mainly an optimizer. It doesn't have a SQL engine and a storage layer. So what it does, so it's distributed as a server which contains the typical components of a database. It has a catalog manager which reads all the tables that are there across all your SQL engines. It also reads the materialized view and cube definitions from its own catalog. It has a JDBC client from which it accepts jars. It has a JDBC jar from which it accepts queries from the users. It uses the cost-based optimizer to figure out what is the best SQL engine and the best storage engine, and then it has a very simple execution engine to redirect the queries to either Hive or a data warehouse or a key value store, for example. And the execution engine is a very thin layer. What it does is it takes care of the query lifecycle management for that particular queries. So it makes sure that it gets the results back from the actual SQL engine and sends it back to the user, or even if there are errors, it makes sure that it's sent back to it. We use Apache Calcite for implementing the optimizer. The Apache Calcite has worked out really well for us. It's an awesome library for plugging in your database rules, your metadata, so on and so forth, and it just comes out with a nice optimized plan from which you can take decisions. We also contributed quite a bit to the Apache Calcite project, mainly in the areas of materialized views. We have made changes in the cubes implementation within Calcite, and we've also done a lot of work on the expression evaluation in the cost-based optimizer, especially for filter clauses and so on and so forth. For example, how can you have a cube on only the last 3 months of data? And we added the feature and kind of gave it back to them. Quark is also available as a service. Since it's from Kubol and Kubol runs it as a service, so Quark is also available as a service. Within Kubol, you can submit Hive queries using something called a Hive command. You can submit Pressure queries using something like a Pressure command, and similarly, there's something called a Quark command from which all the queries that are submitted through this command goes through the Quark layer and decides which SQL engine to run it on in your account. So in terms of roadmap, we have a bunch of work to be done on the optimizer side, especially in the materialized views and the joins area. We are also looking into statistics. We not only want to choose the right copy of the data, but we also want to help you choose the right SQL engine. For example, if the data is lying around in S3, can I use Spark SQL or Presto or Hive, because all of them have access to it? Which one is the best one, right? And there are areas where sometimes there are huge joins and Presto won't work out for you. So can we guess that? Can we guess whether the join or the group by is going to spill over and direct you to the right SQL engine, right? Quark also has to deal with multiple SQL engines. So that means that it should be aware of the various SQL dialects of all the engines that it supports. For example, if you write, if you use from Unix timestamp function in Hive, what does that translate to in Redshift? What does that translate to in Presto? So we have all these mappings with which we can take in queries and rewrite those queries to use the correct SQL dialect when we choose a SQL engine. Similarly, we also have to there's a bunch of work that we are doing to improve the query lifecycle management. When I submit a query to Hive, I have to wait for the results back. How do I do that? That is different from how I have to submit queries to, let's say, Redshift or Presto, and I have to get the results back in a slightly different way, right? So, so we have built a platform where we can encode all these differences, and as we support more and more databases, we'll go and fill in all the rules and the policies and all this stuff to make that happen. One thing that Quark doesn't do is help with ETL. So, you can go ahead and create these materialized views, you can create narrow tables, you can sort the data, so on and so forth, but you also have to keep it refreshed. Every day as new data comes in, you have to go and add this data to the optimized copy or index that you have. That doesn't happen automatically. So what you have, but Quark has the metadata to make this happen. So what we are planning to do is to integrate this with some of the popular workflow engines out there, where we can generate ETL pipelines based on the metadata that we have, and the workflow engines will go ahead and change the add the new data to the optimized copies. So Quark is an open source project. It's released as an Apache. It is released under the Apache license. It is it's on GitHub, and we would definitely love feedback about its features, if it can help folks in using it in their big data stack. It's also an open source project, so we would love to get developers on it and build features, give us ideas about where else this project can go. That's pretty much all I had. It was a pretty short talk. Just want to give an intro to Quark. Any questions?
Can you go back to the architecture diagram once?
Okay.
So the question here is,
how can I turn? Okay, there you go.
in the optimizer.
This one?
Yeah. In the optimizer, if you decide a column, okay, it is going to be efficient. But if it is a PII column, if it is hidden to the user, are you going to recalculate redo the optimization?
So,
did you got my question?
Are you talking about security?
Yes.
How
does the optimizer works on a columns which are secured for use between the users?
So what Quark does is it gets the it gets the metadata from the tables and the columns from, let's say, the Hive meta store or the data warehouse and so on and so forth. So if the user can see the table, it can generate queries on that table, right? And then it just submits it, and we depend upon, let's say, Hive or the Hive security features to to inject those filters to hide particular rows or particular columns, so on and so forth, right? So so if I'm asking for the table and the column metadata as a particular user, we depend upon Hive to not tell us about particular columns, right? So there's no security as such built into Quark. What we depend on is security of the SQL engines that we pull the data from.
Okay. And tools like Tableau or Zoom data, they come with this built-in reports.
Right.
So suppose say if I have business analyst and I have the data in the Hive, if they are connecting to that, so should I connect Tableau to JDBC?
Yes. Yes. So the plan is that you use a JDBC jar to send all queries to Quark. It's either from the command line, or it is from notebook interfaces like Zeppelin or Jupyter, or it is from BI tools like Tableau.
And in the catalog, do you show the metadata of the schema, or do you just some other metadata? Like what metadata is stored in the catalog? Is it like H catalog where you replicate it? What is in the catalog?
Yeah, so it's mainly a cache.
Okay. So how do you sync it up?
Yeah, so we have a time to live, which is about 5 minutes. So what will happen is for the next query, after 5 minutes, we'll go and refresh it. So any changes that are there will show up within 5 minutes. In the worst case, 5 minutes, right? So yeah, so it's a temporary cache. We are not making a copy of it and storing it and so on and so forth. Right? Okay, thank you.